Hello and welcome to helpyourmath.com. In this video, we are going to look at examples of graphing logarithmic functions with reflections and transformations. Before we look at examples, let's review the key characteristics that we look for when we graph logarithmic functions. First, a parent function will have what I call a critical point at 1, 0. Transformed functions, where x is positive, will have a critical point at h plus 1, comma k. And transformed functions where we have a negative x value will be located at h minus 1 comma k. So it's pretty rare that we actually look at a negative x value. That indicates a vertical reflection. That's a reflection about the y-axis. They do exist, however rare they may be, and that's what we would do to locate the critical point. Logarithmic functions have a vertical asymptote. The parent function vertical asymptote will be located at x equals 0, and for any other transformed function, it would be located at x equals h. Lastly, we want to pick values that will create powers of the base in the argument. What that means is we're looking for our arguments, right? So we have this f of x is equal to log base b of x. This is the argument here where x is. We want those to be powers of b. The critical point will be the middle of the pack here, and then we want to pick 2 points that are a little bit smaller than that value and 2 points that are going to be a little bit bigger than that value to help us get a full idea of what this logarithmic function will look like in graph form. Okay, for our first example, we want to graph f of x equals log base 2 of negative x minus 1 plus 3. The first thing we want to do here, because we do have a negative x, is kind of rewrite the argument. So we want to say log base 2 of negative x plus 1 plus 3. Otherwise, we could have an error with determining what the h value is. Now we know that the h value is negative 1 and the k value is positive 3. Using h and k, we can determine that there's a vertical asymptote at x equals h, so we have a vertical asymptote at x equals negative 1. And we have a critical point. This is a special one because this negative x indicates we're going to have a vertical reflection. So remember what this is. It's going to be at h minus 1 comma k. That would be negative 1 minus 1. So it's going to be located at negative 2 comma 3. Okay, the next thing we want to focus on is creating our table of values given we're dealing with base 2. The fact that we're dealing with base 2, I like to first start with the exponents and powers so that I know what I want my arguments to be. So I have my exponent and I have my powers. And the one I know we want to focus on, I like looking at 2 to the negative 2. So I create the exponents to be negative 2, negative 1, 0, 1, and 2. And this one will always be our critical point at that 0. 2 to the negative 2, that would be 1 over 2 squared, or 1/4. 2 to the negative 1 is 1/2. 2 to the 0 is 1. 2 to the 1 is 2. 2 squared is 4. So these are my dream arguments. This is what I want my arguments to be. So I need to figure out the value of x so that I can have those 5 values end up being my argument. So here's what we're going to do. I'm going to create my table of values. I'm not going to fill in anything just yet. What we're going to do is we're going to start with creating an argument of 1/4. So I know I want this negative x minus 1 to equal 1/4. So I want negative x minus 1 to equal 1/4. Now let's solve for x. This would be negative x. I'm going to add 1 to both sides. 1/4 plus 1 is 1 1/4. And let's multiply both sides by negative 1 or divide both sides by negative 1. And we get x is equal to negative 1 1/4. So there's the very first x value for my table. Hooray! Negative 1 1/4. I designed it so that it should turn out to create an argument that is a power of 2. Let's see if I was spot on or not. So we have log base 2, and I'm plugging in negative 1/4 into negative x. So I could either use the one that's given, or I could use the one down here where I rewrote it as negative x plus 1, whatever you're more comfortable with. But either way, negative of negative 1/4 will become positive 1 1/4 minus 1 plus 3. Well, 1 1/4 minus 1 leaves me with 1/4. Is that what I wanted? Yes, it is, because 1/4 is a power of 2. Hooray! This is going to simplify to whatever power of 2 will give me 1/4. Let's go back to my table here. What's going to give me 1/4? if I raise 2 to the negative 2. So this expression is going to simplify to negative 2. Now I have negative 2 plus 3, which equals 1. So we have negative 1 1/4 and 1. Okay, what do we have next? We would like to have 1/2 is my argument. So this was the first one. Now I would like for negative x minus 1 to equal 1/2. So I'm going to do the same thing. I'm going to add 1 to both sides. That's going to give me negative x is equal to 1/2 plus 1 is 1 1/2. Divide both sides by negative 1. The next thing I want to plug in is negative 1 1/2. I'm going to plug that in over here. I am going to run out of space because these are very space-consuming problems. So we're going to do a little bit of work in our head. We picked negative 1 1/2. If I plug it in, negative of negative is going to give me positive 1 1/2. 1 1/2 minus 1 is 1/2. So I have 1/2 here and then plus 3. This is going to simplify to the power I raised 2 to give me 1/2 is my answer. I would have to raise 2 to the negative 1. So this is going to be negative 1 plus 3. That's going to equal 2. So if I plug in negative 1 1/2, I'm going to get a y value of 2. The next point should be my critical point. I like to double check because I like knowing that I have the right answer. So let's verify that this is going to work. What I'm looking for is I would like the argument to equal 1. So I would like for negative x minus 1 to equal 1. That's negative x is equal to 2. That would be x is equal to negative 2. Is that what I said? That is what I said. Hooray! Let's plug in negative 2 and verify that we do end up with 3. So we have log base 2 of, if I plug in negative 2, negative of negative 2 will be positive 2. 2 minus 1 is 1. And then plus 3. So this log base 2 of 1 is going to simplify. What would I have to raise 2 to give me an answer of 1? That would be 2 to the 0. So this becomes 0 plus 3. Yay, it worked. We end up with 3. Ta-ching. There's the critical point. Hooray. Okay, 2 more. These hopefully get a little bit nicer because now we're just dealing with integers as opposed to fractions. Next, we're looking for an argument of 2. I would like negative x minus 1 to equal positive 2. I will add 1 to both sides. I end up with negative x equals 3. So x is equal to negative 3. Okay, let's plug in negative 3 for x. I get log base 2 of negative. That's going to be positive 3. 3 minus 1 is 2. And then what do we have? Plus 3. So what is this going to simplify to? Remember, we're looking for the power we raised 2 to give me 2. That would be 2 to the first. Here we have 1 plus 3, which is equal to 4. So we have negative 3, 4. And last but not least, we would like our argument to equal 4. We would like for negative x minus 1 to equal 4. That would be negative x is equal to 5. That means x will be negative 5. If we plug in negative 5, I'm really running out of space here. Let's create a little room. We have log base 2 of negative. Negative 5 is 5. 5 minus 1 is 4. Yes, that's what we wanted. We wanted an argument of 4. Oh, I said equals. I meant to say plus 3. So what would I raise 2 to give me 4? That would be 2 squared. So we get 2 plus 3, which equals 5. Now we're ready for our graph. Let's start with the vertical asymptote at negative 1. So nothing should be to the right of negative 1. That's why I did all my work over there. And let's plot these points. So this is going to show us a pretty accurate description of what this graph will look like. We have negative 1 1/4, 1. So that's going to be like here, as best I can. Negative 1 1/2, 2 up here. Negative 2, 3 is up here. Negative 3, positive 4. And negative 5, positive 5. Okay, so you can kind of see the shape that this graph takes. I'm going to do the best I can. We know working over a keyboard is a little bit tough for me, but it's kind of smooth. Whoops, and it goes down, 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 down. And there we have it, the graph of f of x equals log base 2 of negative x minus 1 plus 3. All right, let's all take a deep breath before we get started on our very last example. Ready? Okay, let's see what we have here. I notice that we have the negative in front of the logarithm. That indicates we have a reflection about the x-axis. So we don't have to do anything super, super weird. which feels pretty good. Okay, let's label h and k. H is going to equal 3, and k is positive 1. Now let's figure out our vertical asymptote. The vertical asymptote is x equals h, so we have x equals 3. Next, let's identify our critical point. We have nothing fancy here, so it's going to be h plus 1, which is 4, comma k, which is 1. All right, the next thing we want to start thinking about are the powers of 1/4. So we're going to set it up. We have exponents, and we have our powers. So we're going to look at 1/4 to the negative 2, 1/4 to the negative 1, 1/4 to the 0, 1/4 to the 1, and 1/4 squared. Sorry, this goes right over what I was writing. Let's try to keep these separate because I know they're kind of getting squished. Okay, that did not help. Well, it's okay. All right, so what is 1/4 to the negative 2? Well, the negative says take the reciprocal of the base. The reciprocal of 1/4 is 4. That would be 4 squared, so this would be 16. Here we have 1/4 to the negative 1. That's the reciprocal of 1/4, which is 4. 1/4 to the 0 is 1, 1/4 to the 1 is 1/4, and 1/4 squared is 1/16. So right here, this is the dream team of arguments. This is what we want our arguments to ultimately be, so that we have powers of 4, and it's going to make our lives a little bit nicer. We can start our table of values, except we're not going to fill anything in yet. So what's our dream first? Our dream is to have 16 as the argument. The argument right now is x minus 3, so what we're looking for is x minus 3 to equal 16. Well, add 3 to both sides, and we end up with 19. Uh-oh, I don't think this is going to fit on our graph. So we have x equals 19, but that's okay. We'll get a sense of what this looks like. Let's plug that in and see what happens. We get negative log of 1/4. 19 minus 3 is 16, and then we're going to add 1 to that. So this here, log base 1/4 of 16, this is saying 1/4 raised to what power is 16? Right over here, negative 2. But we have negative of negative 2. That's going to end up becoming positive 2, and positive 2 plus 1 is equal to 3. So we end up with 19, comma 3 for our very first point on the graph, except it's not on the graph, our very first point that doesn't fit on the graph. Next, we're looking for an argument of 4. So we want x minus 3 to equal 4. Well, that's going to happen when x equals 7. Hey, this will fit on the graph. Great. So we have 7. And now what we want to do is we want to figure out what the corresponding f of x value is. So this is negative log base 1/4 of 7 minus 3, which is 4, plus 1. This is log base 1/4 of 4. So what power do I raise 1/4 to give me a result of 4? That's right here, negative 1. That negative is different than this negative. This negative is part of our function here. This is negative of negative 1 plus 1. So negative of negative is positive, and 1 plus 1 is equal to 2. Our next one should be the critical point. I always like to double check my work, so let's just make sure. We do end up with the critical point. I hope I don't need that space there. I don't think I do. Let's see. We want x minus 3 to equal 1. That's going to be x equals 4. We're off to a great start here. We plug in 4. If I plug in 4, the argument becomes 1. So I get negative log base 1/4 of 1 plus 1. This thing here, 1/4 raised to what power gives me 1? That's the 0. There's no such thing as negative 0. It's just 0. So we do end up with 4, 1. Yay! There's our critical point. Hooray! Okay, what do we have next? Next, we would like an argument of 1/4. So what do we need to plug in for that? We have x minus 3 is equal to 1/4. I'm going to add 3 to both sides. We end up with 3 and 1/4. So I would like to plug in 3 and 1/4 next. I see we're getting closer to our vertical asymptote. That makes sense. When I plug in 3 and 1/4, I'm going to start working down here. We get negative log, of 1/4. And then we're plugging in 3 and 1/4. 3 and 1/4 minus 3 is 1/4. So we have an argument of 1/4 plus 1. Log base 1/4 of 1/4 is 1, but then we negate it, so we end up with negative 1 plus 1. Look, we found an intercept. 3 and 1/4, comma 0. All right, one more. Are you still with me? I hope so. We're almost there. We would like the argument to be 1/16. How are we going to get 1/16? That would be x minus 3 is equal to 1/16. Let's add 3 to both sides. We end up with 3 and 1/16. So we have 3 and 1/16. If we plug that in, we get negative log base 1/4 of 3 and 1/16 minus 3 is 1/16 plus 1. This here, without that negative, this is saying, what do we have to raise 1/4 to give me a result of 1/16? We would raise it to the second power. However, that negative negates it. We get negative 2 plus 1, which equals negative 1. And there we have it, our complete table of values. Yay! Now comes the fun part, graphing. Let's start with our vertical asymptote at x equals 3. And what do we have? We have 19,3, that's not going to happen. We have 7,2, we can graph that. 7,2 is right here. We have our critical point, 4,1, gorgeous. Next we have 3 and 1/4, 0, maybe like right there. And 3 and 1/16, that's really going to hug the asymptote. It's going to be like right there. Uh-oh, don't end my video. There we go. And we can see this is going up, and then it, up, and then it kind of stalls. And we know we have to get all the way over to 19 before we ever reach that 3. So this is approximately what our logarithmic graph will look like for negative log base 1/4 of x minus 3 plus 1. These have been examples of graphing logarithmic functions with transformations and reflections. Thank you so much for stopping.